Okay, so what we're going to look at in this segment is what happens in real solidification situations. Previously, earlier in the course, we've looked at what happens when we're at equilibrium. So at equilibrium, when you've got enough time for everything to equilibrate at every temperature step, would be when you're cooling quite slowly. And what would happen there, just to review that, would be the following. So if we're at a composition here, that composition there, then we'd start off here all in the liquid. So we'd have a micrograph that would look a little bit like the following. So it would just all be liquid at this particular temperature, temperatures above the melting point of pure A. So then we'd be all in the liquid. Then when we come down to here, we start to enter the alpha plus liquid field, and we form some solid over here of this composition. So at that temperature, we'd start to form some crystals of alpha phase. And as we went down through the alpha plus liquid field, when we came to here, then those crystals would get bigger, those crystals of alpha, and they'd also, their concentration would increase from this point to this point, until finally, when we got to here, we'd all be solid. Those crystals would have grown to the point where they occupied all of the material. So we then have a micrograph that would look, say there were 3 grains in it, 3 grains of alpha, and we're just there in the pure solid alpha phase. And that's the situation for solidification that would happen at, as we went down in temperature, if we were at equilibrium, if the phase diagram applied perfectly. And if we imagine plotting graphs that look a bit like this, so this is a graph of the composition against the volume fraction. So this is the volume fraction going from 0 to 1, and that's the volume fraction. So at the start of the situation, up here in the liquid, at these high temperatures, you've got all liquid, all of this composition, which is the composition of the alloy. So we'll call that C in weight percent or atom percent. Then when we get to this temperature here, we start forming some solid that's got this composition here. So we'll call that composition CS. So that composition CS there, we'd form a little bit of solid, and then when we're down in this situation halfway through solidification, a CS would have got a bit bigger, and we'd have some volume fraction of it according to the Lever rule. Now, what's happened to the liquid? Well, the liquid has become enriched. The liquid's over here at this composition, and the area, that area there, and this area there are the same, so that we're doing our Lever rule balance of conservation of atoms. Until we get further on in solidification, when we go further on and down to a temperature near to the point at which we're pure solid, then we'd be in a situation a bit like this. The composition of the solid would have increased again, and we'd be something like that. That'd be all our solid alpha phase. And then we'd have some liquid that would be very, very enriched, be over at this composition here. So that composition there would be this composition here. And so that's the liquid. And again, a balance would apply such that this bit of solid that's missing here times the volume fraction would be equal to this bit of extra composition there, just from a balance, a conservation of B atoms. So that's the situation for solidification when we're going very slowly. And when we get into a situation where we're going faster, then we'd have a different scenario, because we might not have diffusion in the solid. So we could make another assumption. And the assumption would go something a bit like this. So we'll rub this out. So as we come down in temperature, when we first form some solid, the same thing would happen. We'd form solid that would be at a composition which was given by the phase diagram here. We'd form a little bit of solid that would be at this composition CS. Our alloy composition is still there, and the liquid would therefore enrich a little bit as we came down in temperature once we had an appreciable amount of solid. But what we can say then is we can say, well, okay, let's assume that there is the following, that there is no diffusion in the solid. So that first part of solid to form, its composition is now fixed, it's locked away, but that we have infinitely fast mixing in the liquid phase. Whether that's diffusion or convection or whatever it is, it's moving around so that it can form an infinite mixing. And further, we'll assume that at the interface, so just at this point here between the liquid and solid, at the interface, then equilibrium is observed. So what that means is that then when we come down from this temperature here to this temperature here, well, what will happen? Well, now the composition of the solid, of the next bit of solid that forms, that's now a bit richer. So it's a bit richer. And then back at the interface here, then that means that all of this amount, this area here that's missing, all of that amount, that now goes into the liquid. And so as we go through solidification, we then come down in temperature a bit further. The solid gets a bit richer, that forms at this new lower temperature, and the interface moves along a bit. And then that means that the liquid now has to be even more enriched. So the liquid composition goes up even more, up to that number. And we carry on doing that until we end up running out of liquid, until we've solidified the whole thing. And what that can mean, actually, is that we can get to a situation where we keep enriching the liquid and we go beyond the point in the phase diagram where at equilibrium it would all have finally solidified. So we keep on forming more, so that's the alloy composition, and more rich solid alpha until we're down at this temperature. And the liquid's now very, very enriched. So this is now our liquid here, and all of this is our solid alpha phase. So we can actually have liquid that persists to below the equilibrium temperature at which the liquid would finally go away and we'd enter the pure alpha region. We can end up down here. And we keep on doing that until we got to the eutectic point, in fact. Or if it was a single phase, a single solid phase, then we carry on going until something went wrong with the assumptions, because the composition would keep on going to infinity. So what we're going to do now is we're going to encode those ideas mathematically. So in order to do that, what we're going to do is we're going to define a few things first. So if I take this alpha side of the phase diagram, there's my temperature, and I'll assume that the phase boundaries are given by straight lines. So this is my composition of my liquid as a function of temperature, that's my composition of my solid. Let's call that a solid phase. And at some point, eventually, I get to the eutectic point. So that's my eutectic point, and that's my eutectic temperature. And then down here, eventually, I've got my composition going like this, and that's my pure A. So what we can define here is we can define a ratio K is equal to CS over CL, and that'll be very useful to us later on. That's called the partition coefficient K, and it's always going to be a number less than 1, you can see, because CS always has to be less than CL. And that's, I should probably label my phase fields. That's my liquid, that's my solid, and this is my liquid plus solid, whatever the solid phase is, alpha or whatever it's called. Now here, when we're going through this solidification process, when we're halfway along, let's make this diagram a bit bigger. When we're at some stage in solidification, let's take our alloy composition, which we'll call C. So that's my overall composition. Here's my alloy composition, C. This is my weight. This is my volume fraction of solid, going from 0 to 1, and my volume fraction of liquids therefore going from 0 there to 1 there, but we'll not worry about that. And we'll take little chunks of d volume fraction solid. Try and make them equal size chunks. And then when we go from solidifying a little bit more solid here, so we've got an amount change in volume fraction solid there, then it was liquid before, and what's happened is we've taken this amount and we've shunted that over to give a change in the composition of the liquid. So we've got a change in the composition of the liquid, dCl. And we can therefore write, again as a conservation rule, that this is Cl, that's our volume, that's our composition of our solid at our interface. So the composition of the liquid minus the composition of the solid times dVs, that's this amount here. So that's the amount of solute of B atoms we've rejected into the liquid. And that's caused an increase in the composition of the liquid of VL times dCl. So we've got to spread that over all of this VL here and spread that over our increase in composition of the liquid. So that's just a conservation rule there. And that is just a first order differential equation that we can go ahead and solve. So the other thing we've got to know K will be useful to us in solving the maths. The other thing we need to know is that the volume fraction of solid plus the volume fraction of liquid is equal to 1. Because then we can substitute for one of these guys and get ourselves an equation that we can solve. So we can substitute into that equation and then solve it. So if I come over, if I come over here, then if I substitute into there, I've got Cl minus Cs times dVs, and then I'm going to substitute for volume fraction liquid in there. So I'm going to say that that's equal to 1 minus Vs. So that's equal to 1 minus Vs times dCl. Now the other thing I can do now is I've got something in dCl, so I want to substitute for my Cs in order to get something that I can have just in Cl and Vs. And then I've got a first order differential equation I can solve. So Cs here, Cs is given by, is equal to KCl, right? So I've got Cl minus, that's then KCl times dVs is equal to 1 minus Vs times dCl. So now I can say I've got Cl 1 minus K dVs is equal to 1 minus Vs dCl. Hooray, great. And then I can go away and turn this into a first order differential equation, which I'm going to solve. So now what we can do is we can say, okay, well, we'll take the Cl over here. So we've got my dCl, and I can divide by Cl, bringing that down to here. And I can take my Vs, and I can divide it, my dVs here, and I can divide by 1 minus Vs. And then I've just got a 1 minus K over here. And that's then something we can just integrate up and solve. So I can put an integral sign through. So 1 minus K, integrate dVs divided by 1 minus Vs is equal to the integral of dCl by Cl. So now we need to think about what the limits on our integration are going to be. Well, we're integrating from a VS of volume fraction of solid of 0 up to some number. So that's from 0 up to wherever we're at in solidification so far, VS. And we're integrating from a composition of our liquid. Well, it starts off at the alloy composition C up to whatever the composition of the liquid is at this point in the solidification process. So then we've got our limits, and we can integrate that, and we just solve that integral, and we're away. So now we solve that integral, and we've got 1 minus k times the log of 1 minus Vs. And when we differentiate that, we get 1 over 1 minus Vs, and we get a minus sign out. So we've got a minus sign there between 0 and Vs is equal to the log of Cl, that's what the integral of 1 over Cl is, between Cl and C. So now I can take my minus sign out here and have k minus 1. And I've got log of 1 minus Vs minus the log of 1 minus 0, so log of 1. And then I've got log Cl minus log of C. So then I can say, well, the log of 1 is 0, so that goes away. And then I've got the log of Cl over C, and I've got k minus 1 times the log of 1 minus Vs. Now, if I raise that to the power of e, so I'm going to come over up to here. If I raise that to the power of e, I'll have 1 minus Vs to the k minus 1, because I can bring the k in as a multiple in my log, and is equal to Cl over C. And that's going to be then our solution. And so finally we can say that the composition of the liquid is equal to C times 1 minus Vs to the k minus 1. And if we wanted to know the solid composition, because we can't really measure the liquid composition after we've finished the solidification process, what we're interested in is what's the variation in the solid composition. So we can come back and take our K is equal to CS over CL, and we can plug that into there. So we can then say CS is equal to KCl, so we've got K times this thing, so CS is equal to K times C. We're just going to get a multiple of k, 1 minus Vs to the k minus 1. Now, so that's our final solution, if you like. And that's called the Scheil equation, after the person who first derived it. So it's worth asking ourselves now, what does this mean? Well, k minus 1, notice that's a number between 0 and 1 minus 1. So that's a negative power that is between 0 and minus 1 in total, that term. So that's something that's a 1 over sort of a situation. So what that's going to look like, if we look at this, what this plays out as, when we come back to our composition against volume fraction graph, so that's pure volume fraction of solid from 0 to 1. We've got our alloy composition here that is C. And we've got an original composition K times C for CS. When you put 0 in here, that's 1 to the power of something which is equal to 1. So we've got KC at the initial state, but the volume fraction of solid is equal to 0. And then this will go up something like this. That's what our solid composition will do. And our liquid composition, well, it just does C times 1 minus Vs. So our liquid composition does that, Cl. So that's what the Scheil equation looks like. That's what the solution looks like. So what that's saying is that over the course of solidification, then the composition of the two phases will go up and up and up and up. And what will happen is that at some point the composition of the liquid will equal the eutectic composition. So when we come back here, this will keep on going down until, as we go down in temperature, the composition of the liquid will keep on increasing until we get to the eutectic point. And at that point, then with this little triangle construction doesn't work anymore. And so what we'll get to the point is that the composition of the liquid will get to the eutectic. So say this is the eutectic composition of the eutectic here. So we'll call this number here the composition of the eutectic. And at that point, wherever that is, it won't necessarily coincide with the initial alloy composition. So I'll actually make it slightly higher so that it doesn't. Let's say that's the composition of the eutectic. It can't go beyond that. At that point, then this whole derivation stops applying, and then the remaining solid is then, so that's all our alpha phase that's solidified, and then the remaining liquid here that was all at this composition becomes a eutectic mixture. So it becomes those plates of alpha and whatever it is, beta phase in our case here. So that becomes eutectic at the end. And because this equation goes off to infinity, then you'll always get a eutectic here in a binary eutectic phase diagram that's solidifying under Scheil. So what effectively we're saying is that the Scheil equation forms the other bound. So there are two limits bounding solidification. You can have equilibrium solidification, and that's where you have diffusion in both phases, both the solid and the liquid. And we have Scheil, where we have no diffusion in the solid and fast mixing in the liquid. And those form two limits. Reality will fall somewhere in between those two things. And therefore, but in the Scheil case, then we will always have a eutectic form. The other thing this says to you is that you will tend to have a variation in composition in the solid that forms. So by now, many of you will have done a lab where you've seen solidification happen. You've seen solidification where the crystals grow as dendrites, probably from the walls of the container that act as the nucleation sites. So what this looks like, we'll show in a picture here, which shows the solidification of an aluminium alloy. You can anodize aluminium alloys to give you pretty colors and interference contrast when you look at it in an optical microscope. And you see there you've got a variation in the coloration of the solidified crystals, of the dendrites. And that variation in coloration reflects a variation in composition, reflects this effect. And this effect is called coring. So here we've got a picture of coring shown on a single dendrite, and you can see that the center of the dendrite's black, and at the edge of the dendrite towards the end of solidification, where the composition has come up, then it's etched slightly white, and then at the very end of solidification, we've got some eutectic that's formed. And that's a very common situation for industrial castings, because they tend to be solidified quite fast, and that's called coring. So in the Scheil situation, you have solidification where it varies like that, and you can do calculations with that, and you'll get a variation in composition until you get a final eutectic, and that's the message really for this segment. So Scheil always predicts a eutectic, and here's another example here, where you can see the eutectic quite nicely. You can't see the coring as well, but there's another example there, where Scheil always predicts a eutectic, even when at equilibrium solidification, then you would come, as we in our first case here, you would come into the pure solid phase. Our first case over here. So when in equilibrium you come into the pure solid, then in Scheil solidification you'll always get to the eutectic point, and you'll always get a eutectic formed, and you'll always see it in a micrograph. So if you see a eutectic in an alloy that should have entered at equilibrium pure solid, then it's evidence that diffusion in the solid has been quite limited, and you solidified, therefore, quite quickly. You didn't have a lot of time to reach equilibrium. And the last thing we can do is we can do an example with this, where we can find what the volume fraction of eutectic is going to be. So let's do that. So we'll take our result here, and we'll ask ourselves, at what point, we'll actually take this result here, at what point does the composition of the liquid hit the eutectic composition? So we can say that if we, in fact, we'll take logs again. We'll say that the log of Cl over C is equal to K minus 1 times the log of 1 minus Vs. So that's the log of 1 minus Vs. But that's equal to the volume fraction of liquid. And at the eutectic point, that's the volume fraction of the liquid that turns into eutectic. So that's equal to VL, which if we're considering the eutectic, that's equal to VE. And that composition of the liquid will then be VE at the eutectic. At the eutectic point. And then we can deal with this by saying, okay, let's say that VE, if we take exponentials here, then we can work that out. So VE is going to be the exponential. We'll have a curly bracket. So we'll divide that by K minus 1. That comes down here. The log of the composition of the eutectic divided by the alloy composition. And that will be our solution for the volume fraction of eutectic that forms in Scheil solidification. And we can ask ourselves at some other point in solidification, if we were, at a temperature somewhere in our phase diagram. So if we come over here, if we said, well, at this temperature here, well, we know we can look from the phase diagram at what the composition of the liquid must be, and therefore we can go and plug that composition for the liquid into our result, and then find out how much solid we would have formed at that point in solidification, and solve various problems. And that we'll do that in some of the question sheets. So that's the Scheil equation, and that's how we deal with solidification in the case where things start to go fast. So what we've started to do here is we've started to go beyond pure equilibrium phase diagrams and think about other situations. The equilibrium phase diagrams you see are still useful, and they're useful because we're in a situation where we are making some assumptions where equilibrium still applies at the interface. So it's a foundational point that we can use to come out and look at more complex situations. Now, one or two little things, caveats to think about. One is, if we think about this phase diagram. So this is temperature, that's pure A, that's pure B, two atoms A and B, whatever they are. That's the weight percent of B. That's our liquid L. That's our solid S. And that's our solid plus liquid region. Now, we can still do the Scheil derivation here, and it would be exactly the same. We would say, well, okay, we'll assume that this is a straight line somehow, and then we'll find a K as being CS over CL. And you notice actually here, K is changing a little bit because these lines aren't really straight. But you could make some assumption and make it work. But the problem would be that CS and CL will keep going to infinity, and they can't go to infinity because the composition can only go to 1. It can only become pure B. Once it's got no meaning beyond that. So it's physically unreasonable. So beyond fractions of solid, beyond maybe 80 or 90%, then this Scheil derivation starts to be physically unreasonable, even in the situations where you don't have eutectics. Once you go beyond about 80% volume fraction solid, then it will start to be a physically unreasonable derivation to apply. So you've got to take care when applying it at high volume fractions of solid. Now, the last thing, and this will get us into the next segment, the last thing is to think about what happens to our core dendrites. The problem we've got is that our core dendrites here, they have a eutectic in between, and that eutectic will always melt at the eutectic temperature. And we don't necessarily want that in our alloy. Also, say we wanted a solid alpha phase alloy, we don't want to have that other beta phase there necessarily. And so what we want to do if we solidified it and we've got that is we want to get rid of that eutectic and we want to get rid of that variation in composition in the dendrites. So what we do is we take it up in temperature, up probably quite close to the eutectic point, so up to some temperature like here. I'll just draw that on. So up to some temperature just below the eutectic. And we do what's called homogenizations. Homogenize. So what you do in a homogenizer, in a food blender, is you equalize everything everywhere. You get rid of all of the structural variations. And that's what a homogenization heat treatment is. It's where you're equalizing out the composition everywhere in our micrograph there, in our dendrites, and getting rid of that eutectic, getting rid of the variation in composition through the solid, and getting to a situation where all of the solid has the same composition. And that might take anything up to a day. So in a nickel superalloy, you might do a homogenization heat treatment at something like 1300 degrees C for a day, which is very expensive in furnace time. But it's a way to get the alloy that we wanted to make when we were originally melting it up. And then we can go through and do whatever heat treatments we need to do after that to develop the microstructure we want at the nanoscale. And that's how we get rid of what's called this segregation, this variation in composition, is we do a homogenization heat treatment. But we'll look a bit more at diffusion in the next segment.